Hello, everyone. Thanks for coming. Help yourselves to snacks and beverages and such. There's coffee. There's flavored polar beverages and fruits. Sorry, vegetables and yeah. So help yourself, and help yourself during the presentation as well. Yep. It is upstairs in my desk. Yeah. Yeah. Yuri and James are both there. And should they disappear for some reason, or should there be issues and you can't reach me through Skype, hopefully you can reach out to one of the other committee members who can alert me. Can't believe it's already time. Just yesterday, I was accepted. Well, no, actually. Yeah, go ahead, go ahead. Yeah, you can take photos. We'll see. Undecided on that. We'll see. No, well, I'll probably dress up for that too. That's fine.
All right, so thanks everybody. So Rod for some time turns out officially so it's the lab.
The lab. No, not the department. Talk to Rod about that, because I am far from holding the record.
So I feel less bad. But John has done a tremendous amount of good work during
No.
No, all of it?
I'm going to touch upon everything, even if it's just briefly.
So hang on. All right.
Thanks, Emery, for that wonderful introduction. So, like Emery said, I'm going to discuss my dissertation today, which aims to write web development. So first, some introductions are in order. This is Brett. Brett is the lead developer of Slacks, a web application that lets you chat with your colleagues. And like most startups in Silicon Valley, Slacks fully embraces Facebook's move fast and break things mentality, but to an extreme degree, because they move too fast and now their product is broken, and Brett is having a very, very bad day. Let's travel back to earlier in the morning. Brett is enjoying his mug of coffee when his developer Chad comes running in, shouting that picture messages are broken. This is sort of the standard way he files bug reports. Let's look at this bug in detail. So Slacks let users attach images to the messages that they send by including a URL in their post. And Chad discovered that the pictures are sometimes associated with the incorrect chat message. So here, there should be a beach picture with the first message, but both of them are lumped together on the second one. The way this feature should work is as follows. A user types a message with the URL and hits the enter key, and this creates a JavaScript keyboard event, which processes that enter key. Slacks reacts by displaying the message and telling the browser to load the picture. The browser loads this image as a background task. Once the picture loads, the browser emits a JavaScript load event, and Slacks displays it inside of the chat room. This process repeats for subsequent image messages. So far, this looks great. It looks like it's working properly. The problem is, users can enter picture messages way faster than they can be downloaded from the internet, which causes the images to appear on the wrong messages. We just witnessed a race condition in JavaScript. Brett does not know that there is a race condition. He just knows that there is a bug. So he decides to use the browser's existing stepping debugger to investigate. He sets a breakpoint in the code. He enters an image message into the chat room and hits enter. And he single steps through the JavaScript using step forward and such to try and see what's going on. The code tells the browser to download the image. And at this point, even though the JavaScript code is completely paused on a breakpoint, it's not doing anything, it's just paused. The browser's tasks continue uninhibited in parallel with this thing being paused. So as a result of this, the image loads in the background before Brett even makes a few steps in the debugger, because humans are very slow at this sort of task. So as a result, Brett always sees the good execution while debugging. The debugger is effectively hiding all of the buggy event schedules, like these ones, due to human latency. So the problem with the debugger is that it focuses entirely on the JavaScript half of execution, and it completely ignores tasks happening in the browser. Brett makes no progress on fixing the bug, and he quickly forgets about it as he sees Chad running in once more. Slacks becomes unbearably slow during long sessions. So Brett, once again, begins an investigation. After using Slacks for a while, Brett notices that it becomes slow and unresponsive, and it takes a very long time to load new chat rooms. And eventually, the browser crashes because it's out of memory. Slacks appears to have a memory leak. Today, the process of debugging these memory leaks is arduous. Developers typically examine and compare heap snapshots that display the live objects of the program. So here's a real heap snapshot from Airbnb.com, which is a website that we have discovered has many memory leaks. Two of these object types are internal browser objects that the website code does not directly manage. They're completely unhelpful for the developer. The other two contain every array in the program and every object of an unnamed type. And unnamed objects happen often because JavaScript is dynamically typed and some things are just objects with no name. And if I expand the view a bit, I'll see random names like XN that mean absolutely nothing to the developer, since the source code of most production web applications, like Slacks and Airbnb, are minified and obfuscated to reduce the size of JavaScript code in the program. What is not evident in this view is which objects are actually leaking. Where is the memory leak? Finding and fixing these memory leaks is a huge challenge even for seasoned developers. A Google developer closed a Google Maps memory leak that over 100 developers voted on, easily among one of their highest ranked bug reports, because it was infeasible to fix and debug the leak. So Brett spends hours looking at heap snapshots and is unable to find or fix the bug. And Chad comes running in again with an emergency. Customers are complaining that Slacks is using much more network bandwidth than anticipated. So Brett returns to debugging. He runs the website under Chrome's development tools and looks at the network log. The largest item at the top is a 3 megabyte image, which is not good for Slacks on mobile. Brett opens this URL to see what it's loading and finds that it's a large picture of an overfed squirrel. Brett has no idea why this is happening. It's not hosted on Slacks' domain either. It's hosted on sqrl.com. Going back to the log, Brett notices that the initiator of this request is a data URL. This is an asynchronous way to evaluate JavaScript code. The data URL literally encodes the source code that is being run on the web page. It happens a lot in advertisements and such. In other words, some HTML or JavaScript file on the web page, we don't know who, created a script element with this data URL, which caused the JavaScript encoded in the URL to run on the web page, which downloaded the large picture of a large squirrel. So we don't know what is doing this. This information leads Brett to another question, which I just asked. What actually did this? What inserted this data URL that loaded the squirrel? One promising feature of Chrome's developer tools is async call stacks. Normally, JavaScript debuggers only show you the call stack from the current JavaScript event. So basically, all of the functions that were called from the event that is currently running. Context from prior events that cause the one that's currently happening are completely lost. To help with asynchronous debugging tasks, Chrome's debugger extends the call stack into previous events. So this asynchronous call stack, which is sort of an example I'm showing, shows that the current JavaScript event was caused by a timer created with set timeout right here. Brett quite reasonably expects that an async call stack would reveal the mystery code because it is the thing that is causing the squirrel to appear. The networking tab of Chrome's developer tools actually captures an async call stack for every request. If you hover over this initiator, it shows it. But the async call stack reveals absolutely nothing new. It just says that this data URL showed the image, and that's all the information Brett has. Brett has encountered a severe limitation of this feature. Async call stacks do not support asynchrony through the DOM. They do not track asynchronous control flow through like the HTML and such that are on the web page. So now Brett still has no idea why Slacks is fetching the squirrel picture, and Chad swears he did not do it. There we go. Brett is undercaffeinated, stressed, and overworked. He spots Chad in the distance and considers his life choices. So Chad runs in, shouting, "We have too many customers and we can't scale. They've gone from 10 customers to 11, which is too much for their Ruby server. It needs to be replaced." So Chad just burns out. Slacks does not have the cash to finance a scalable rewrite. They're game over. In an ideal world, Brett would be able to replace this existing Ruby server with one that is known to work and scale, namely IRC. IRC does not speak in JSON messages like Slack's Ruby server, though. It has its own custom protocol. Brett would normally resolve this problem by using some existing library that knows how to speak this protocol. But these libraries are written in conventional languages like Java. Writing a new library for the web is out of the question because the IRC protocol is decades old and really gnarly. So there's just a lot that is hard to understand, and the specifications are not very good. So it would be reasonable to think that Brett could somehow compile code that understands the IRC protocol to JavaScript, namely compile Java to JavaScript. But this is not generally possible. These programs typically use a dedicated thread for connecting to servers, but browsers are single-threaded. They use a file system to store logs, but browsers don't have file systems. They also use TCP sockets to actually talk to each IRC server, but browsers lack those as well. In short, browsers lack the environment that this code expects, which prevents direct translation to JavaScript. So browser development tools have completely failed this startup. Each of the tools examined use techniques intended for conventional programming environments, which ignore the unique complications of the browser environment. In short, these tools are ineffective for the problems that web developers face. So in this dissertation, I aim to write web development with a complete set of development tools. McFly is the first time-traveling debugger for web applications. It reproduces browser task and GUI non-determinism, so Brett can debug a buggy execution without worrying about the debugger changing program behavior. McFly also forms the foundation of a new JavaScript time-traveling debugger by Microsoft. Bleak is the first automatic memory leak debugger for web applications. Given a short input script, Bleak automatically locates memory leaks and identifies their root causes in the source code. Guided by Bleak, I have found and fixed over 50 new memory leaks in production web applications and libraries, including the ones on this slide. Because traces a web application's execution and builds a causal graph of asynchronous program behavior. Because would lead Brett to the mystery code responsible for fetching this squirrel picture. Finally, Doppio and Browsix emulate POSIX and Unix, respectively, resources in the browser. They make it possible to bring existing code, like the IRC library written in Java, into the browser. And over 30 million visitors to the Internet Archive have used Doppio to run legacy software in the browser. I actually think it's closer to 50 million. Together, these tools form an effective foundation for web development. So let's rewind the clock, and we'll return to Brett's first issue. What sort of debugging experience would Brett like to have? First, after observing a buggy execution, like the one that's showing right now, Brett would like to step back in time to figure out what caused it. And when he does this, he would like the GUI to reflect the current state of the program, so he can reconcile the JavaScript code he's looking at with what is actually happening on screen. What Brett wants is a time-traveling debugger with full support for web applications. But there are currently no time-traveling debuggers for web applications. Existing time-traveling debuggers are for programs written in conventional programming languages, like C, C++, and C#. These time-traveling debuggers typically take what's called the record and replay approach to debugging. Let's take a look at this. During execution, these debuggers record a log of non-deterministic input to the program, such as reads from disk. And with the log alone, the debugger can replay a recorded execution to seek to a specific program state. But it would always need to replay from the beginning of the execution. To make time travel tractable, these systems introduce periodic checkpoints that contain the program's entire state. So now, to travel to a particular point in the program's execution, a line at a certain time, the debugger loads up the nearest checkpoint and plays the execution forward until it arrives at the target. This design sounds promising, but these debuggers have one major limitation, and that is they don't support the program's visual state during time travel. If I were to port these debuggers to the browser, Brett would not see Slack's messages on the screen while he moves backward in time. He would not see Slack's GUI at all while debugging. The debugger would only let Brett look at JavaScript state, which is not helpful for debugging this bug. At this point, you may be wondering if time traveling the visual state may be possible. However, a web application's visual state and all other input and output to the program is managed by the browser's layout engine, which is external to the JavaScript engine. For example, when Slack invokes a DOM API, which controls the GUI, to insert an image, beach.jpg, it informs the layout engine what it did, and the layout engine then fetches the image from the network and updates the display with no JavaScript code involved at all. It just does this on behalf of the web application. Another challenge is concurrency. The layout engine can update the visual state in parallel with JavaScript execution. So for example, the layout engine updates animated GUI events, animated GUI elements independent of JavaScript execution. At any point during this animation, JavaScript code can request information like the size of the smallest rectangle that encloses this particular element. And this value depends on the state of the animation. So in order to time travel a web application and its visual state, the debugger needs to time travel the layout engine as well and keep it in sync with JavaScript execution so that it gets the same values when it performs these operations. The layout engine is quite complex, though. All of its state is stored in C++ objects inside the browser. All major web browsers are written in C++. The layout engine is also multi-threaded and sometimes multi-process. And the layout engine has the complexity and size of an operating system. So significant modifications to the layout engine are infeasible and not portable to other web browsers. However, the layout engine already exposes a significant amount of its internal state via JavaScript interfaces that are standard across all major browsers. So for example, the DOM interface exposes most of the GUI state to JavaScript. When needed state is not available, we can extend these existing interfaces with privileged debugger-only extensions. This would let a debugger query and modify hidden state in the hidden visual state, such as the current frame or state of an animation. As a bonus, this design is portable across web browsers because it extends standardized interfaces. So this idea forms the core of McFly, and I implemented these extensions in the Microsoft Edge web browser and used them to build McFly, which is the first time traveling debugger for web applications. McFly record, replays, and checkpoints JavaScript and layout engine state, which enables it to support visual state during time travel. Like previous debuggers, McFly implements debugger features like step backward on top of checkpoints and an event log, but it uses an optimization to make the common case faster. The first time a developer steps backward, McFly replays the animation from the nearest checkpoint and plays forward until the JavaScript event just prior to the time travel target. At this point, McFly takes a new program checkpoint because it can do this during replay, and it continues on to the target. Subsequent backward steps will use the new closer checkpoint. So as a result, the first time a developer hits step backward, there is a one-time setup cost to create that checkpoint. And from then on, it's much faster. And you can read more details about McFly and the extensions we made in chapter 3 of my dissertation. For now, I'm going to proceed to some of the highlights of the evaluation. We evaluated our McFly prototype on a set of benchmarks from the web that use popular libraries and exercise various features. In particular, Pac-Man contains an 80 millisecond game loop that generates many events as the user plays the game. On the benchmark applications, McFly takes 0.36 seconds on average to initiate replay from a checkpoint. And this action dominates the cost of stepping backward in the common case, meaning after the setup cost is paid. So stepping backward typically takes less than half a second. The first step backwards, which creates that new checkpoint, takes an average of 3.8 seconds to complete. And that's in a configuration where McFly already takes a checkpoint every 2 seconds during the execution. And in the same configuration, McFly slows down the benchmark applications by an average of only 4%. And that's during the recording phase when you're initially recording the session with the application. Using McFly, Brett initiates time travel debugging after noticing the bug and reverse steps until he locates the cause, a lack of synchronization on GUI updates. And Chad now thinks Brett is a wizard, but we all know his secret. Now, Brett has to deal with a second issue, long sessions becoming slow due to memory leaks. Before I dive into memory leaks on the web, I want to ask you all a philosophical question, but don't answer. What are memory leaks anyway? And you might think that the answer is obvious, but it's actually surprisingly subtle. Let's consider manual memory management in a language like C. When a developer needs some precious valuable memory, they call malloc. If the program no longer needs that memory, the developer needs to call free to let it go. Sometimes the program has memory that looks valuable and in use, but it's actually worthless, like an ineffective cache, and it could be safely freed without actually impacting the program. It's up to the developer to determine when memory becomes garbage or worthless and to call free to release it. If the developer doesn't free some garbage or some worthless memory, it sticks around. And if this continues to happen, the program's heap becomes like an episode of Hoarders. In manual memory management land, failing to free garbage or worthless memory causes memory leaks. Automatic memory management ensures that certain kinds of leaks can't happen. Memory that is valuable to the program is reachable, and the garbage collector keeps this reachable memory around. When the memory becomes unreachable and starts to pile up, the garbage collector kicks in and automatically throws it away, ensuring that garbage does not stick around. What about worthless memory? If garbage is automatically collected, can a program have worthless memory? Turns out, yes, it can. Automatic memory management does not solve the problem of memory leaks caused by worthless memory. Just because memory is reachable does not mean that it is actually valuable. As a result, worthless memory can pile up just fine in a garbage collected system. One approach for identifying worthless memory is staleness tracking. Objects become fresh when they are used and eventually become stale if they haven't been accessed recently. Stale objects are marked as potential memory leaks. Another approach to locate worthless memory is growth analysis. Growth analysis locates objects that grow in count or in size, assuming that continually growing things are unintentional and are likely memory leaks. Neither of these approaches are a silver bullet for finding memory leaks in the presence of automatic memory management. Worthless memory can be reachable and accessed frequently by an application, and a staleness-based approach will not find these leaking objects. Also, object growth does not always indicate a memory leak. Some growth is desirable, such as caches. Growth-based approaches may incorrectly mark these objects as leaks. What we really want is a semantics-based definition of a memory leak. An object source is leaking if deleting some of the objects does not impact the program's behavior, which indicates that the objects are in fact worthless, and if it retains an unbounded number of objects over time. However, there's a problem with this definition. How can we tell that the number of objects is actually unbounded and that they have no impact on the program's behavior? What we need is some sort of an oracle. This is the oracle at Delphi. An oracle promises to identify leak object sources and say, hey, what's with all this smoke up here? Get rid of it. You don't need it. It's a leak. We actually managed to find ourselves an oracle. And what it told us really surprised us. It told us that everything is leaking. Many websites and the libraries they use suffer from memory leaks that degrade browser responsiveness over time. In fact, over 99% of Google Chrome crashes on low-end Android smartphones are due to out-of-memory issues. These problems aren't just a matter of speed. They can prevent visitors from spending time on a website. And we've already discussed that debugging memory leaks with heap snapshots is arduous, even for Google developers. Snapshots do not make it evident where worthless objects are and where the heap is actually growing, which heap items are actually unneeded and can be deleted. Things are looking quite bleak for debugging memory leaks in web applications. However, there is hope. Most modern single-page web applications, such as Airbnb, Gmail, and weather.com, frequently return to the same visual state. And by visual state, I mean a literal view that the application presents to the user, typically corresponding to a particular screen. On Airbnb, I can click between oh, sorry about that. Pretend you did not see this yet. Okay. So on Airbnb, I can click between a listing of homes for rent and a list of recommendations tailored specifically for me. And these screens are the core output of the web application. If the application's heap exhibits sustained growth after each visit to a specific screen, then the application likely has a memory leak. In other words, growth between visits to the same screen is a strong indicator of a leak. And this growth can be used as an oracle to identify worthless memory. This insight is central to Bleak, an automatic memory leak debugger for web applications. Bleak appeared at PLDI 2018. Bleak uses growth between round trips to the same visual state as an oracle to identify leaking objects. And because we have this oracle, Bleak exhibits high precision. On a corpus of real production web applications, over 90% of the leaks reported are true leaks. The leaks that Bleak find also have high impact. We've found large leaks in production web applications. Bleak also identifies the source code that is directly responsible for causing each leak, which dramatically simplifies the process of fixing them. To use Bleak, a developer must write a short input script of about 40 lines of code, which I will describe momentarily, and that drives the application in some loop through distinct visual states. This is the sole input to Bleak. The rest of the process is completely automatic. This is the input script that I wrote for Airbnb, and I don't expect any of you to read this, but note that it's only 17 lines of code long. The script forms a simple visual state machine, if you will, where each visual state has a check and a next function. I'm going to briefly look at one of these states. This is the visual state corresponding to the Airbnb page for recommendations just for me. The check function returns true when the application has finished drawing the visual state. In this case, it's quite simple. It verifies that the For You link at the top of the web page is selected, like so. The next function transitions the application into the next visual state. And for Airbnb, it just clicks on the Homes link in the top navigation. Zooming back out, Bleak executes this input script in the following manner. Bleak first waits for the application to load and display the For You screen. It then transitions to the Home screen. Bleak waits for the application to finish displaying the Home screen before transitioning back to the For You screen. And with this, the loop is closed, and now Bleak can run the application in a loop. As mentioned before, the developer only needs to provide that short input script to Bleak, and the rest of that process is completely automatic. Bleak loads the application in Chrome and commands the browser via the remote debugging protocol. Chrome is configured to talk to a Bleak-controlled proxy, which performs JavaScript rewriting needed for memory leak debugging. And with this architecture, Bleak can diagnose memory leaks in unmodified production web applications that we don't control, like Airbnb. And using Bleak, I have found, reported, and fixed over 50 memory leaks in a wide variety of popular web applications and the libraries that they use. And that includes Airbnb, AngularJS, jQuery, and other things. All of these leaks were completely unknown to us and to application developers. Bleak identifies memory leaks by looking for growing objects in the heap between round trips to a visual state. I want to stress that a heap graph alone does not make these memory leaks obvious. So here's actually the heap graph for About Blank, which is a completely blank web page. It has tens of thousands of nodes and edges. And all of these just correspond to built-in browser objects. There's nothing on this web page. The heap graph for Airbnb looks like this. This is the actual screenshot. Yeah. Sure. Why it's like that? Yeah, sure. It looks like this because there are a large variety of existing JavaScript interfaces like HTML image element, HTML element, image, etc. And all of these are in the environment as objects that you invoke. Yes, the constructor for these things. All of the methods on them are also objects. All of the properties are objects that contain other objects that contain functions. So that it's all just the built-in functionality. It's that rich. And there's just a lot of extraneous objects. So yeah, this is Airbnb's graph. And this is actually a graphing program, Gephi, which just can't display it. There are over 800,000 nodes and 4 million edges. So we have no idea what in this is causing memory leaks. And for the purpose of this presentation, I'm going to dramatically simplify the view so that the memory leak becomes extremely obvious. But while I do that, I want you to keep this image in mind because these leaks are far from obvious just given a heap snapshot. The first visit to Airbnb's home screen yields a heap graph like the following. Again, simplified. Using the developer-provided input script, Vilk runs the application in a loop back to the same screen and takes another snapshot. So now you may notice 3 objects have grown since the last visit. Vilk marks these as potential memory leak routes. Vilk repeats the process multiple times, typically for a total of 8 round trips, to filter out objects that grow and stop growing. They just grow to a fixed size. At the end of this process, Vilk identifies a set of leak routes which are responsible for leaking memory, worthless memory, like these 3 map objects. We had no idea that these were actually leaking in the first place. In a non-simplified heap graph, each of these maps is actually a very large subgraph that contains many hundreds of small objects. So this leak, again, was far from obvious in the heap graph. So now that Vilk has identified leak routes, things that are growing to an unbounded degree, it needs to rank them by importance so developers can spend their time fixing leaks that actually matter. And while I'm only showing 3 leak routes on the slide, there may be many more for the developer to prioritize. In fact, we found 32 distinct leak routes on Airbnb.com. One possible ranking metric is called retained size, which is the quantity of memory that would be collected if you garbage collected a leak route, if you just removed it from the program. This is the standard metric that many tools already use. The global variables, window and document, are not garbage collectible, so they're not relevant at all to this metric. So the problem with this metric is that objects shared between leak routes, like these large map objects, they're not captured at all by this metric, because fixing a single one of the leak routes will not garbage collect any of these maps. And so no leak route gets credit for them. As a result, retained size actually ranks the history leak route, which is an array of strings, very small, above the event listener leaks, which leak the very large map objects. Essentially, retained size misrepresents the impact of leaks. So instead, Vilk uses a new metric that we created called leak share to measure the impact of memory leaks. Leak share splits the credit for objects shared between leak routes. The algorithm is pretty conceptually simple. First, leak share ignores objects that are reachable from objects that are not leak routes, because they're just not leaked objects. Second, for each remaining object, leak share counts the number of leak routes that retain it. So in this example, each map is retained by 2 leak routes, while everything else is only retained by 1. Third, leak share splits the credit for each object evenly between the leak routes that retain it. The end result is that the event listener lists, which leak very large map objects, are correctly ranked above the history array. So leak share focuses developer effort on memory leaks that provide the biggest return on investment, meaning the developer spends less time to free more memory. To diagnose memory leaks, Vilk reruns the application in a loop and collects stack traces when leak routes grow. Vilk collects a stack trace when the application adds an item to a leak route, and if that item is later removed, Vilk removes the stack trace that it collected for that item. And to collect these stack traces, Vilk uses JavaScript reflection and program transformations. And these stack traces point directly to the source code responsible for each memory leak. At the end of a Bleak run, Bleak produces an interactive report that describes its findings. So on this slide is the report that Bleak produced for Airbnb.com during our evaluation. It's too small to actually read, but I'll show you the highlights. First, it shows you the impact of the leaks on the heap size in this nice graph form. It ranks the leaks that it found by leak share and displays them in this list. And then it also highlights the source code in the source code viewer that is directly responsible for each leak. So now developers can go and figure out what's causing leaks and fix them. Overall, Bleak reported 32 leak routes for Airbnb.com. And of these, only 2 were false positives, corresponding to objects that grow to a fixed size, but we didn't observe that fixed size during the run. Using Bleak's output, I was able to implement fixes for each of these leaks in this obfuscated production web application and test them locally by injecting them into the web page with Bleak's proxy. Each fix took about 10 minutes to develop because the source code just pointed directly to the code that was responsible. And fixing all of these leaks eliminated over a megabyte of heap growth per return visit to the home screen, which reduced heap growth by over 80%. And guided by Bleak, I was able to develop a fix for the Google Maps memory leak that the developer couldn't figure out. I provided the developers with all the information required to fix the bug in the official bug report. We also ran Bleak on a variety of other production web applications. This line represents live heap size over round trips to a specific visual state with no leak fixes in place. You can clearly see from the slope of the line that all these applications have memory leaks. This dotted green line is the live heap size after fixing all of the leaks that Bleak reported. We don't know how many leaks there are that Bleak did not find, but it's clear that fixing the leaks significantly decreased heap growth. And in fact, fixing Bleak reported leaks reduced heap growth by an average of 94% across these applications. Bleak provides Brett with all the information he needs to fix the memory leaks in Slacks. Slacks is now leaner and faster than ever. So now, although Slacks is no longer leaking significant amounts of memory, it's still wasting bandwidth with pictures of squirrels, and Brad has no idea why. Perhaps in this case, a causal graph could be useful for solving this problem. Causal graphs are a useful tool for understanding the behavior of complex systems. Here's an example causal graph of a web application's execution. The 2 nodes on the left represent JavaScript events, and each directed edge represents that event A caused event B with the labeled program action, such as setting the source of a script element. If Brett had this causal graph, he could use it to identify the mystery code, which would actually be identified here, except that actually caused the squirrel picture to be downloaded. However, no existing tools can create this causal graph, and the browser poses several challenges to doing so. One challenge is that the cause of each event is not always clear. Each JavaScript event is triggered by some previous event or some input-output event. Here is a JavaScript event log captured while Slack, the actual Slack that we all know and love, or hate, initializes. And there are hundreds of events. From a log alone, it's not clear why each event is happening in the first place and how any of these events are actually related. And the causes of each event are buried within standards documents. This section right here describes the condition under which image elements emit load events. Another challenge is third-party code. Web applications frequently embed obfuscated libraries and advertisement code. Here's the list of domains that weather.com loads content from. Many of these are related to advertisements. The black boxes that you see at the end of the list are iframes, and they embed third-party HTML that loads more third-party content and more HTML. And just to reiterate, all this code is completely minified and obfuscated. This is real JavaScript code that I found on the webpage of weather.com. It just like, it does some encryption or something. It's just decrypting JavaScript from a string using this logic. A tool that produces a causal graph must be able to reason about obfuscated code and include it in the causal graph. A causal graph that only tracks JavaScript execution only tells half of the story. Web applications contain a decent amount of HTML, and the contents of HTML directly affect JavaScript execution and program behavior. Consider this snippet of HTML. It loads a JavaScript file called add.js. First, it creates an HTML script element in the GUI that JavaScript can interact with. It initiates an HTTP request to a server to download add.js. It emits a load or an error event on the script element, depending on if it successfully downloaded that file. And it executes some JavaScript code that is contained in add.js. This type of behavior is not limited to script elements and script tags either. There are other HTML tags that exhibit similar behavior. Overall, any tool that attempts to understand JavaScript execution needs full support for HTML in the DOM. However, there is some hope. All of the browser's JavaScript interfaces are described using WebIDL, or Web Interface Description Language. WebIDL is standardized, and all modern web standards use it to describe new browser interfaces. And these interfaces accurately reflect how browsers implement the standards. Most browsers actually use WebIDL to automatically generate C++ code that binds JavaScript environment to the browser's code. And then also the WebIDL spec supports annotations, so you can annotate items in a WebIDL description. And some browsers already use this for their code generation that I just mentioned. So for example, Chrome annotates any JavaScript property that corresponds to an HTML attribute. WebIDL is great because it relates JavaScript objects to events in HTML. For example, here's a truncated HTML image element interface, which reflects an image HTML tag in the HTML. This description reveals important information about this object. The interface reveals that this object emits a load event at some point with this event handler property. It also reveals, through Chrome's specific annotations, that these object properties are reflected in the HTML and can be set as attributes on the image tag. And so this provides a crucial link between JavaScript and HTML. From the standards documents, we can manually decode that setting the source property of an image eventually causes a load event to occur. And then also from WebIDL, we know that the source property can be set both in JavaScript through setting the source property on the object and in HTML itself by including source in the tag. So using WebIDL, we can infer most causal relations between JavaScript events and add annotations to specify the rest. And this idea forms the, oh yes. Yes. So I'm going to go into the different types of JavaScript interfaces and what you need to infer and what you need to manually specify. The source part needs to be manually specified, but from this specification alone, we know that you have to set this load handler before load will actually ever be observed. So there are some causal relations that you can automatically infer just from the idea. Yes. Yeah, exactly. And there's only a small number of, relatively small number of these annotations you have to manually write. Most of them are automatically inferred. So this idea forms the core of bcause, a framework for understanding asynchronous control flow in web applications. Bcause produces a trace of a web application's behavior while the developer interacts with it in an unmodified web browser. Bcause uses the trace to produce a causal graph of JavaScript events. And since bcause tracks event causality through HTML and the DOM, these graphs have no broken causal chains. All JavaScript events are directly or indirectly related to the web application's initial HTML document that loaded when you typed in the URL and hit enter. The primary component to bcause is its hook generator. given a set of WebIDL files with causality annotations, because produces a JavaScript file called hooks.js. And these hooks use JavaScript reflection to intercept and log important program actions. The hook generation process occurs offline. The developer uses because by opening their web application in Chrome and interacting with it just like normal. In the background, Chrome connects to the because proxy, which intercepts Chrome's network connections. The proxy rewrites the web application's JavaScript and HTML so that the hooks load before the web application does, so it can intercept all of its behavior. The hooks send trace events to a server, which stores them into a trace file on disk. This entire process operates on unmodified production web applications, like weather.com, and includes all of their obfuscated third-party dependencies. So they're all included in the causal graph that you can form from this. Because traces contain the sequence of JavaScript events, HTML initializations, and causal relations observed during the program execution. A web application's execution begins with some root HTML file. And these two trace entries indicate the start and end of an HTML document initializing. In general, start and end entries refer to a specific JavaScript event or HTML initialization. In between start and end log entries are program actions that cause future events or causal relations. This entry specifies that app.html contains a script tag pointing to app.js, which causes script initialization. The log continues with a set of start and end entries that are bookending causal relation entries. Translating a because trace into a causal graph is relatively straightforward. Start and end entries combine to form nodes, like so. And the causal relations form outgoing edges from the node they occurred during to the node they caused. Any causal relations that indicate events that did not occur or were not observed by the program are ignored. And this happens because there are some things like a script element pointing to app.js that may cause a load event if the network download succeeds properly, or an error event if it fails to load.
Hi, John.
Yeah.
Can you explain how this relates to things like Polaris, which does like data flow analysis at a very low level, like looking at right DOM state? But should I think that type of logging as 80% of what you're doing, but you're looking at sort of the most interesting part of that, or is there another way that I should think about it?
So Polaris tracks the mutations of the DOM back to program actions, if I remember correctly. It doesn't track the causality of events in a JavaScript execution. Is that correct?
Well, so kind of. This is what I'm trying to tease out. So
Yep.
So what Polaris will do is that will actually instrument all the reads and writes, let's say, each JavaScript variable.
Yep.
Or X declared, in JavaScript. It'll also look at reads and writes, image.source or things like that. That was a low-level data flow trace. Now, in and of itself, it won't be causality, right? You have to build a tool like that atop the low-level data flow log. But I guess I'm wondering, how I should compare and contrast the approach of looking at these low-level read writes approach that you're using, which seems more high-level.
Yes.
What are you gaining? What are you missing? So on and so forth.
Yeah, the approach that I'm using is much more high level. I'm not logging every read or write that the program makes to main memory or to the DOM. I am using the WebIDL to target specific actions that are known to cause events. So my log is less comprehensive than yours, but it's much more high level, which makes it really easy to build the causal graph like I showed. So it may be possible that using Polaris that you could extract more high level information from it. But I am just logging high-level information. I'd have to look more at what you're doing in particular to see if there's anything that I'm logging that you're not.
Okay, thank you.
Yep. All right. So because causal graphs display 4 types of browser events as nodes: DOM events, asynchronous operations, HTML and script initialization, and cross-document messages. I will briefly describe how because supports each. DOM events are named events that occur on objects. two things must happen before a DOM event actually occurs. The web application must register an event handler for that particular event, and the event must actually happen in the first place. Because uses WebIDL to infer which program actions register event handlers. They're just indicated through event handler properties and stuff like that. And I manually annotate program actions that trigger events. There are also some events that don't have program actions that trigger them. For example, clicking on an element is triggered by the user clicking and not by the program doing something. So specifically, I add a fires annotation to WebIDL attributes and operations that may cause DOM events. This annotation states that setting the source property on an image element may cause a load event on the image. Overall, I added 66 annotations. Yep. Oh, so there are some actions that fire an event on a sub-property. So for example, XML HTTP request has an upload property that also emits events as you do certain types of posts and such. There's some other things like firing events on return values. Yeah, this is very much the common case. There's only a couple exceptions. I just wanted to show you the real deal. This is literally what I added. And so I added 66 annotations like this over 22 different interfaces. And if I ignore IndexedDB, which has a very large number of DOM event-driven interfaces, it's a unique flower, I only added 42 annotations across 16 interfaces, and that covers sort of the core of the DOM. Well, it's hard to know. Since it's specified within these web standards that are just plain English, I may have missed some. But if I missed them, it's very easy to add them in just using that annotation. Yeah. Yeah, it's hard to determine how good coverage is, because there are some events that just happen without any intervention from the program, like clicking. Asynchronous operations are tasks that occur in parallel with JavaScript execution. Asynchronous operations are callback-based or promise-based. Callback-based operations accept one or more JavaScript functions as arguments, and the browser invokes these functions 0 or more times as the operation proceeds. Promise-based operations are more modern, and that's what we're seeing in emerging browser interfaces. They return what's called a promise object, and JavaScript code can pass a function to the promise object that gets invoked once the operation completes. Both interface styles involve passing functions that the browser later invokes, and the only program action that causes these functions to get invoked is calling this asynchronous operation interface in the first place. Because uses static type information within WebIDL to automatically find and intercept these asynchronous operations. Specifically, callback-based operations accept functions as arguments, and promise-based operations return promise objects. And no manual annotations are required to support them. A few program actions cause the browser to asynchronously initialize additional HTML and JavaScript. I have listed all of them here on the slide, and I just manually annotated the WebIDL for these interfaces to indicate that they trigger HTML or script initialization. In addition, the proxy already modifies all HTML and JavaScript to indicate the start and end of their initialization. Finally, JavaScript code can use post-message interfaces to communicate across different domains. So when slacks.com wants to send a message to sqrl.com, it uses post-message to send the message. Because adds a unique ID to the message, which lets it track the source of each message. And although there are multiple browser interfaces that contain post-message functions, like message board and window, they are annotated with the post-message annotation already within Chrome. So because uses this attribute to infer which interfaces support post-message and to intercept them and handle them appropriately. To demonstrate the utility of all this, of because, I built AdBlame, which is a tool that uses Bcause's causal graphs to estimate the bandwidth consumption of web apps with ad blocking enabled. And before I explain how ad blame works, it's important to understand how ad blockers work and why this is a challenging task. Ad blockers use filter lists to specify which web content to block. If a web application tries to load a resource that matches an entry in the list, the ad blocker blocks the network request and prevents it from loading. Had the ad actually loaded, it might have pulled in additional advertising resources. But since the ad blocker ensures that this never happened, these resources do not need to be explicitly blocked by filter lists. Ad blame is given the causal graph from a run of the web app with ads enabled and a set of filter lists. Running the filter list on the graph would only block ad.js. Ad blame then uses the causal information in the causal graph to determine which network requests depend on blocked content and to remove them from the bandwidth estimation. And ad blame extends bcause's traces with network request entries that track program actions that initiate network requests. Only 10 annotations are required, plus integration with the proxy to measure the size of network requests on the wire. And I evaluate ad blame on the home pages of 3 ad-heavy websites: weather.com, cnn.com, and dictionary.com. I compare ad blame against a baseline approach that runs the web application's network requests through a filter list and determines which will be blocked that way. And to gather ground truth, I collect a network log while Chrome visits the website with ublock origin enabled. And in all of these configurations, I use the easy list and easy privacy filter lists, which are comprehensive and they're supported across all major ad blockers. Like I said, all of these benchmark apps are ad-heavy websites. And just to underscore that fact, this is the bandwidth consumption of all of the websites with ads enabled. And this is the bandwidth consumption with the ad blocker enabled. In all cases, there is a significant gap. And there's also a significant possibility for error in these estimations. These green lines are ad blame's prediction given a causal graph of an execution with ads. It's within 2.2% of the ground truth. Finally, the black lines show the baseline prediction, demonstrating that filter lists do not contain many of the resources that ads actually pull in. This baseline is within 50% of ground truth. It's not a very good estimation. Using bcause, Brett, yep. So the difference is, like I said, ad resources that are fetched by ad code that's directly embedded on the web page are not contained in filter lists. For what? Oh, that. So ad blame doesn't have complete information about which network request should be associated with which. No, actually, the main thing is there may be sources of network requests that I am missing. Sometimes there are other interfaces that might be invoked that I might be missing. In addition, see, I'm also modeling the behavior of a cache. I'm making certain assumptions that GET requests are cached after the first time they happen, and that may be invalid in some scenarios. And finally, there's also some non-determinism involved. I'm visiting the web page twice, once with bcause and once with ublock origin. So there may be some slight variation in the network requests that actually happen across the executions. Arjun? So yeah, that's the use of this tool. The use of bcause is that now you can build tools like this one that are enhanced with the causal graph. So this is sort of just a use case where this is a hard problem if you don't just run the web page under a particular ad blocker filter lists. You can also offline try different policies to see how they would impact the network, the bandwidth overhead. So we were considering, let's see. Yeah, so there were some other use cases like using the log to figure out good ad blocking strategies, to identify, to monitor what ads are doing on the web page. So enhancing the causal graph with known malicious actions or actions that may be malicious or bandwidth usage or CPU usage to see what actually is the cost of ads on like mobile phones, on desktops, etc. So those were some of the ideas that we were spitballing. Right. So another thing is just program understanding. So using because, Brett figured out why Slacks was fetching the large image of the squirrel. This is one thing you can also do with because. Slacks contains Google Ads, which loaded an ad that injected the JavaScript that fetched the squirrel. So Brett changed Slacks' ad preferences to blacklist the ad from appearing, which dramatically reduced Slacks' bandwidth consumption. Brett's feeling good right now after fixing so many bugs today. And he is ready to migrate Slacks' Ruby server to IRC. This part will take less than 10 minutes. I could not do it and just go to the end, or I could do it. How are people feeling? I know this is rather long. All right, let's go for it. To make this transition, Brett would like to take an off-the-shelf IRC client library written in Java and run it in the browser. The Slacks frontend would then use the library to communicate with IRC servers. But as I mentioned before, this is not generally possible. The browser lacks many of the resources that these clients expect. Specifically, it lacks threads, a file system, and network sockets, which are all used by this library. Doppio emulates POSIX resources in the browser, which makes it possible to bring conventional languages and their applications to the browser. Doppio appeared at PLVI 2014. It won the Distinguished Software Artifact Award and was selected as a SIGPlan research highlight. Doppio provides an execution environment that emulates multi-threading on top of browser events. And Doppio also provides operating system services, including a file system, TCP sockets, and stuff like that, that are emulated at the top existing browser interfaces. Using Doppio, I implemented Doppio JVM, which is a full-featured Java virtual machine interpreter written in JavaScript that can run unmodified JVM programs and Java programs directly in the browser. Using Doppio JVM, Brett can run this IRC client library in the browser. When the IRC client opens a socket to the IRC server, the JVM uses Doppio sockets to open a WebSocket connection. And on the server side, Brett uses WebSockify to act as a bridge between WebSockets and TCP sockets, which aren't directly compatible. And that lets the IRC client transparently talk to the IRC server. When the IRC client writes log files, the JVM actually uses Doppio's file system. The file system has multiple possible backends, including browser local storage and Dropbox cloud storage. And so the files are stored there. Essentially, the program believes it is running in the native environment and functions identically in the browser and running on your computer. And that enables it to function in the browser with no modifications. It just runs in the browser. You can read more details about Doppio in chapter 6 of my dissertation. And so, Doppio has completely solved, wait, is that Chad? Uh-oh. Uh-oh. He's right. Doppio JVM requires a complete copy of Java's core libraries, the Java class library. And that's a very large download. That would not be good on mobile. And also, weak mobile devices might not want to run a full JVM in JavaScript. What Brett would like to do to solve this problem is offload the IRC client library to the server when it detects that there's a mobile device. In this scenario, Slacks would communicate with some HTTP server that's sort of an adapter / front end to this. And this would solve the problem on mobile. Now you're running it on a server and everything's fine. But the problem is it would complicate Slacks' code base, which is shared across mobile and desktop. The Slacks client would now need to support talking directly to the library in Doppio, and also talking to the library indirectly through HTTP requests. And that adds considerable maintenance burden to Slacks. So Brett then has a brilliant idea. Why not run this server client side, right? You run it in the browser. Then Slacks would use the same logic across all devices. On desktop, it runs the server in the browser. And on mobile, it runs it on the server. Seems good, right? But unfortunately, this is not possible with just Doppio. Doppio only provides single program operating system services. If we tried to run both of these things in the browser, they would each receive a separate copy of Doppio's operating system services. And so while they can use Doppio sockets to talk to the IRC server if they want to, they can't communicate with each other. What we need is some centralized thing that coordinates access to shared operating system resources. And that thing is called BrowseX. BrowseX bridges the gap between Unix and the browser. And this work appeared at ASPOS 2017. BrowseX implements a shared file system, pipes, and sockets on top of existing browser resources. These live inside of the BrowseX kernel, which controls access to these resources. The kernel can spawn BrowseX processes, which run programs like the adapter, HTTP server, and the IRC client on dedicated hardware threads. These processes communicate with the kernel and access BrowseX's operating system resources through BrowseX system calls. The kernel itself runs alongside an ordinary web page as a JavaScript library. And like Doppio, all of this takes place completely within an unmodified web browser, so it's sandboxed just like any other web page that you would visit. I don't have time today to really discuss all of this, but you can read more details about BrowseX in Chapter 7 of my dissertation. BrowseX enables Slacks to bring a multi-process system into the browser. When Slacks detects that it is running on a beefy desktop system, Slacks uses BrowseX to run the adapter and the IRC client library in the browser. They can then use familiar Unix abstractions to communicate with each other. So in addition, the Slacks client can send HTTP requests to the adapter through BrowseX sockets. All of this runs completely in the browser. And on mobile, the items running in BrowseX are seamlessly offloaded to the server, enabling the client to share the logic for sending these HTTP requests across desktop and mobile. For more information on using BrowseX for seamlessly running server-side workloads in the browser, see the meme generator case study in section 7.3 of my dissertation. Thanks to Doppio and BrowseX, Slacks has successfully and quickly migrated their backend to IRC. Brett now embraces a new philosophy: move fast, but break less often. Brett is very happy. Using a complete suite of tools and techniques designed for the browser, he was able to overcome many challenges that threatened his startup. The only thing we couldn't fix today is Slack's bottom line. So during this defense, somehow I have managed to discuss all 5 tools that I've developed during my PhD that help developers debug, optimize, understand, and write web applications. Together, these form an effective foundation for web development. Thank you all for your attention. That's it. Woo.